In this recording, I'm going to walk through some of the code for our Module 1 notebook. So here's where we have the GitHub for the Machine Learning for Spectral Imaging book. If we go into book modules, we'll see module running here. That's what we're going to run. If you want to download it from GitHub, get a code. I usually do open with GitHub desktop, and that helps manage things. So assuming you've downloaded the code, here's the code on the right-hand side, which I have open in VS Code. Let's go ahead and run some of these things, and we're going to walk through pretty much line by line. So this first block, standard first block in Python, we import our modules. Here's matplotlib. If you're ever not sure, and this is really a good thing to do if first time you see a module or something in Python, do a search, look for the documentation on that thing. So matplotlib is a really useful package, very common for making plots in Python. All right, so if you're not familiar, you can go see some of the examples of different types of plots that we can make with matplotlib. NumPy is a numerical Python package. We often import it as NP because we use it a lot. So NP gives us a nice abbreviation. Copy, we'll see when we use that. Import spectral. We can take a look at that. And it turns out spectrals are common words, so I'm going to search for spectral in Python. And so here's the documentation for spectral Python. So this is a package for reading and writing and working with hyperspectral imagery. And then something that I think is really important is to get used to writing your own packages that you can import. And so this is called scripts _M1, M1 because we're looking at module 1. And so if you write a .py or a .python file, you can put it in the same folder as your notebook, and you can import it. And so all the commands that are in this module M1 will be imported into your notebook. And so, sorry. So from scripts M1, we import star means I import all the functions. And really the only function I want here is this function here, which uses some of the other functions. We don't need to get into what's in this Python file for now. Okay, so that runs this, and this code, this download Washington, D.C. image, you only have to run it once. If you've already run it like I've already run it here, it's not going to do anything when you run it. If you haven't run it, it will create a folder up here called spectral images, which has the Washington, D.C. image. And that's a hyperspectral image, so we'll need to do a little work to open it up. Right? So you can't view it with standard image software. Okay, so part 1, we're going to open the image and load it as a NumPy array. So here's that spectral Python that I have on the left-hand side. And so here's some coding notes. So we'll go through it line by line. So this F name, spectral images, Washington, D.C. there. So if I go here and I say, I can right click and say, copy the relative path, which is the path to this file. And so there's I guess that's most of the path. The relative path is usually, doesn't have this piece. So there's the path to that file, and you'll notice that that's the same as the path that's right here. That's our file name. Okay, so that's just the file name for that file. And then this spectral, so we're using the spectral package, we're using the NV module in there, and we're going to open the image. And so we have this file name and then this .hdr file and then the file name. If we go up here, you'll notice there's this, which I can't open in Python. It's a binary file. It just has data. And then this has this .hdr as a header file. It has the header information. So information of when this file was made. The samples, which is the number of columns in the image. Lines is the number of lines or rows of data in the image. Samples and lines are a kind of a computer screen image, digital image language. A line is like a row of pixels in the image. Bands is the number of bands. Then This tells us whether it's float, float 32, float 64, integer data, it's the data type. Interleave has to do with whether the data has been saved, values like reading across the rows first or the whole pixel at once. These things, you can look them up if you want more details on those. Generally, we don't need to get into these samples, lines, and bands, get read into the data when we read them in Python. Here's the wavelengths for our data. And then here's what's called BBL, that's a bad bands list. So if there's a 0 in one of these spots, it's an indicator that this band is bad for some reason. It's not a band that you would want to use. Okay. For now, we don't need to get into that. That's just what this spectral package uses to load our image. Okay, so now, so I have this this variable IM, and this variable IM, we can see what's inside of that, right? So when it reads it in, it's not just a single value. It's has information connected to that. It's called a class. And so it's im.n rows is going to give me the number of rows. im.n columns will give me the number of columns in the image. im.n bands will give me the number of bands. im.bands has all the information about the bands, and then .centers is going to give us the centers for the wavelengths. Something you can do if you want to see the variables in memory. So I put a debug point in and I hit debug. You can look and we can see the, let me enlarge this. You can see the variables that we have in memory over on the left-hand side here. So NP is a NumPy module. Here's IM, which is our variable that we read in. So this IM here comes from IM, tells us the data type, and what we come down here, there's a number of bands, number of columns, number of rows. There's a fair amount in here that you don't need. Bands, shape. Here in under IM, we can go into the bands, which is a has information contained within it. So IM bands, and then you can go down. The centers is the centers for the wavelengths, and then there's additional information. Okay, so I'm going to get out of the debug mode. And just go ahead and run that. Okay, so here's the output from these commands. And something you'll notice, this command, when I say print, it prints this. I put an F in front of my quotes. F says I'm going to have some variables in this text, and I'm going to put those variables inside of these curly braces. And when we have a variable inside the curly braces, it tells Python to convert that to a string so we can output it in that location. All right, so if I didn't put the curly braces in, right, and really if I didn't have this F, it would just print that name. So the alternative way to print that is I could go to the end of the string, and you'll often see this. I can do plus, which means append to my previous string, str, which means convert to string. So that'll convert this value into a string and then print it out there. That's an equivalent way to write it. I like putting an F at the beginning, and then you can have your variables inside the curly braces. Okay, so that's how to print some of the data. Now, a challenge with working with hyperspectral images, large images, sometimes they're large, and this is large files in general. You often don't want to load all the data in memory on your computer at the same time. In this case, the file isn't tremendous, so I'm going to load it all in the memory at once. So I'll use this imload command, and notice it took 0.4 seconds, tiny bit of time. My computer's pretty quick, whereas up here, 0.3 seconds. So we loaded that data into memory, and now imr is an array. So if I want to say, what's imr, it's a NumPy array, and notice it's data type float 32. We've seen a couple of spots where data type comes up float 32, gives you decimal precision. It's pretty good. Doesn't take as much memory as a float 64, so it's a good trade-off. And we don't want to display all the data here, right? It has 1280 rows, 307 columns, 156 bands. So NumPy will truncate it so it doesn't display all the data. And if we want the shape, typical for a NumPy array, we can do dot shape, and that'll give us the shape, right? Rows, columns, and other dimensions for a multi-dimensional array. Okay, so we've said this is an image. So let's start looking at it as an image. So this would be sort of a naive way to plot it. We're not going to do much prep. We're going to say, okay, I'm going to take band 50. Now, if I look back to the header file, just up here, and I look at these bands and I count 50 over, right? 1, 2, 3, 4, 5, 6. So I don't know, it's about 830 nanometers is the wavelength for what we're going to look at. So this says, take the image array, take all rows, all columns, that's what that colon means, and put 50 in here, and then show this as an image. So this is this plot imshow. So if I wasn't sure what imshow meant, I could go to the matplotlib documentation. And search for imshow. And this would tell me all the information on imshow. A good place to go when you search for something. Geeks for Geeks has a really good presentation, so that's often a good place to go to look at a command in Python. There's a couple of sites that'll come up commonly, of course, Stack Overflow, that you should get used to. Okay, so this is going to show this as an image, right? Just to show us what we're looking at. If I take this piece by itself and I put 50 in here, right? That's an array, and if I want to look at the shape of that array, there's its shape. 1280 columns, 1280 rows, 307 columns, and one dimension. Sometimes we need to get rid of that extra dimension, and there's a NumPy command for that, and it's np.squeeze. So if we squeeze that array and then get the shape, it's going to get rid of that extra column. So if that ever causes a problem, the squeeze command will take care of that. Or if you see squeeze anywhere, just know it's getting rid of extra dimensions that are only a 1 that aren't really needed. Right. Okay, so here's how we show this as an image. And here's our image. But it doesn't look much. For one, it's small on my screen. I can change that by setting the figure size. Right, so there's a bigger figure size, so I can see what's going on here. But of course, it's not very nice to look at. It just looks, it's like shades of blue, right? So it doesn't look much like an image. So the first thing we want to do to get it to fit on the screen better is to rotate it 90 degrees. So here's that rotated 90 degrees. So we rotate it 90 degrees, and there's this, one of the things working with images, the way I showed the image here, it goes from 0 at the top, counting down through the rows, and that's the way you reference the location of pixels, and the left is 0. So the origin is in the top left, the rows go down, columns go left to right across the top. That's a standard way to reference pixels when you're displaying them in the image. We want to rotate it 90 degrees. And we can do that with this numpy.rotate that'll rotate the array. The problem is when we do that, it changes where the location of the top left would be. So it would be going down and then over. But when we rotate it, we still want, right, if we look at this dark area is where we want the origin, the top left. So when we rotate it, we now actually want the origin to be at the left side, but at the bottom, and columns go in that direction. So doing this flip and rotate will keep the column and row indices organized. So when we look at a spot here, we can read off where the column and the row is. Not something you generally have to care about, but it's taken care of here. Also, we set the color map to gray, which is going to give us a grayscale image. And that's okay, but there's no color, right? And so we could pick, right? I could pick a different band. So I could take band 100. Right, that would give me a different image. Or I could make band 10. And so we've said there's lots of different bands. There's, how many? We had the number up here. There's 156 different bands. So that could be anywhere from 0 to 155. What did I have? I had it as 50 before. But now we want to make a red, green, blue image. And we've said that the red color corresponds to a wavelength that's about 640. Green color corresponds to 550. Blue color corresponds to 460. So what we want to do is we want to look at these wavelengths. Here's a set of wavelengths. So this WL is a set of wavelengths. Up above, it was im.bands.centers. And I don't want to have to type im.bands.centers every time I want the wavelength. Right, there's my wavelengths. That's kind of cumbersome. I want to just type WL. And I want it to be a NumPy array. So this NumPy converts, this is actually a list. It converts it to a NumPy array, which allows us to use NumPy to work with it. So now WL, the NumPy array, displays, I think, a little more nicely. Tells us it's an array. And we can get the wavelength for like band 50. We're going to just put 50 in as the index into that. And it's 725 nanometers is the index. This is a block of code that it's worth taking a moment to understand. So if I look at np.absolute value wavelength minus 640, this takes the wavelength array, and this is one of the things that's nice about working with NumPy arrays as opposed to lists, is we can do some mathematical operations on the NumPy arrays. It takes all these values, it subtracts off 640. So if we just did WL minus 640, we'd get this. We subtract 640 from every one of these, and you can see here is where it switches from positive to negative. So the band that's closest to 640 would be one of those two bands. Right, it's I guess this one here is the one that's closest to 640. So this subtracts 640 off. It takes the absolute value of that difference, and if we print that, we'll get this. And this is in scientific notation. So you really want to look at the exponents, and when they get small and just kind of skimming through, they're getting smaller. I don't know, maybe this is the smallest value, so that might be where the band that's closest to 640 occurs. But we want to know where that occurs, and so what we do is we do this. We want to say argmin says give me the argument of the minimum, or give me the index for the minimum for this NP, the absolute value of the wavelength minus 640. right? And so that says band 41 is going to be the band that has a wavelength that's closest to 640, and I could say what's the wavelength at 41, band 41. And it's found the band that's close to 640. Okay, so that's what these do. This says the red index is going to be 41, and here's the wavelength. Green is 28, and there's the wavelength. And then blue is 10, and there's the wavelength. So now, to make a red, green, blue image, we take the image array. We're going to take all rows, all columns, and these three bands. And if we run this, you'll notice if I want to, I guess I have to run this block here. If I want to tinker with code, I'll often copy and paste it into a new line. And if I want to get the shape of this, right, so it should have the same number of rows and columns as our original image, but rows and columns, but now it's going to have three bands. So just for comparison, here's the full image, and it has a number of rows and columns and 156 bands. Okay, so this gives us this imRGB, which is the array for the RGB image. And I can do imshow to show it. I have to rotate it and do this thing that adjusts the ticks, the labels, to get my labels to line up nicely. Actually, so that would be the way to get the axes to line up with the origin in the right spot. But if you look at this, there's not much to show, right? A couple of problems. This image, it's not on a 0 to 1 scale, so I could do np.max. Right, what's the maximum value for this red, green, blue image? Right, it's this. So NumPy automatically clips the data because the values have to either be between 0 to 1 for floats, which is our case, or 0 to 255 for integers. So it's not going to display the data properly. What we can do is we can modify each band. So this is going to iterate through the bands. So here we create the image, we iterate through the bands. We modify each band so that this imRGB is going to be between 0 to 1. So first we subtract off the minimum value for that band, and then we divide by the maximum value of the band, like after subtracting from the minimum. So that's going to switch us from, let's go ahead and run this. Initially, before we do this normalization step, the maximum value is this, right? That's what we get as an output from this print command. Maximum value is 9877 in band with index 0. And now, after we do this normalization, the new maximum, which is what's going to get printed here, is 1, which is what we want. So now we've taken each band and scaled it so it has a minimum of 0 and a maximum of 1. And we get this, which is an okay image, but this doesn't look great, right? If it just looks dark, right? You shouldn't look at it. It looks too dark. So really what's going on here, and this is something your camera takes care of when you take a picture for looking at, is the darkest 2% of pixels and the brightest 2%. Usually we take all the brightest 2% and set them to whatever the maximum value is, the darkest 2%, and set them to a value of 0. And this does sometimes it's called color stretching. It's what your eye does when you adjust. You walk into a new room, if the room's kind of dark, your eye will open up the iris and will adjust how much light it's letting through. And so here's how we do this. And before we walk through the code, let's just take a look at the outputs here. So these are histograms. So let's just study the red. So what this is telling us is the red pixel values range between 0 and around 10,000. Right? If we go up here, the maximum was 9,877. So that's the brightest red, right? The highest value we get for red. So it's close to 10,000. So the pixels range from 0 to 10,000. If you look at most of the bright values, they're in this kind of 0 to 4,000 range or so. So what we want to do is not scale everything so that a 10,000 corresponds to the brightest, but come down and truncate off the top 2% of the data to where this blue line is. This blue line shows us the 2% threshold, and take everything out here and set it to the value of wherever the blue line is, and use this range of values for what we're going to show as our range in red. And now you can see the data is better spread out, and it's going to look visually a lot better. And so that's what we do in each of these. So this is the original data, the raw data, and this is after we do what's called a 2% stretch. And now we do a 2% stretch, we clip off the top 2%, and we get this, which is clearly a much better image, right? Compare this to what's up here, that's too dark. So let's walk through this line by line. So this builds our mRGB. This sets up figure access. It says we're going to build some subplots. We have 1 row and 3 columns in this figure, and this figure is going to give us this. How do I select it? That it's going to plot this series of plots. So subplots says we're going to have 1 row with 3 columns of plots. We give this title, and this is going to be the kind of the full title for the figure, right? That's across the top. Then we're going to iterate through red, green, and blue, and CLR is going to be the name of the color we're going to iterate through, and I will be the index for that color in our array. So mRGB index I, we flatten it. So let's see what flattening does. All right, so there's our array, and let's, I don't know, band 0, right, just to put an index in there. And if we do shape, there's the shape of that array. If we flatten it and then do shape, so let's do dot flatten. So flatten the array and then take its shape. We get that what the flattened array is, 1 array with that many values in it. And that's the same as number of rows times number of columns. I forget if I created something. Sometimes I'll rename this n rows so it's easier to access, but I guess I didn't. So we'll print this, and then we'll print this. And we see that they should be the same. Yeah, so the number of values there is the number of rows times the number of columns, right? So flattening takes your 2-dimensional array and just makes it a very long vector. And that's often useful for processing your data. So we turn it into a vector. This uses the np percentile command. It says give me the bottom 2 percentile. Then we do this again. We get the 98th percentile, and that gives us the lower threshold and the upper threshold. This AX V line. So this is give me a vertical line that extends across the axes, and put that on the plot. And so that's what creates these blue lines. We're going to set our X label and Y label. Those are the what it says pixel value and count. So it's good to put a title and label your axes. It says put a grid on the plot, and then we're going to plot those. This plot type layout, it reorganizes the margins so that the data looks, generally it helps the data look nice, the plots look nice. Then we're going to clip the array, and so here's what we're going to call image RGB clipped. And to do the clipping, we compute again the lower threshold and upper threshold, and instead of just plotting the blue lines, we take each band, we subtract off the lower threshold, then first thing we do is we take everywhere in this band where you're lower than the lower threshold, and we set it equal to the lower threshold. Everywhere in the band that's greater than the upper threshold, and set that equal to the upper threshold. Then we subtract the lowest value, and we divide by the maximum to rescale it to 0 to 1. And we, in a sense, we pull out this band from the 3-band image, so just a single band, so we can do these computations on that, and then we save that back into the image array. And then here's where we do the plot for the histogram. And this .hist, that's a matplotlib histogram. So it says, give me a histogram of this data. I flattened it with 100 bins, and CLR is the color. Now, there's two ways you can create plots in matplotlib. One is to do what we did up here. You do plt.imshow, right? Imshow says show me an image. So you can do a plt.plot or whatever your plotting command is, or you can do the name of the axes and then do dot. We could do .imshow or dot. In this case, we're creating a histogram or do you plot on the axes. This allows us to do the plot on a specific axis. In this case, we have 3 subplots, so when we want to make these plots, we want to be able to tell it which axes to put that on. Okay, so that gives us the color stretching, and here's our nice image. And if we pull out just one band and make a grayscale image, we can see what is a much nicer grayscale image. And just if we do the non-clipped version, right, it's too dark. But the clipped version or the 2% stretched version gives us a nice image. Oh, and it looks like maybe I didn't run this block to actually create the clipped version in my memory. If you ever need to run this button will execute everything, run all cells above the cell I'm looking at. So if I need to rerun those to prepare my data to be able to work with it here, that's a useful. This executes everything below the cell I'm working at. Okay, so part 3, we want to look at a pixel spectra. And so we set up this location 200, 178, and that's, I looked around in the image and I figured out row 200, column 178 will give me a pixel in the vegetation there. And if I want to, I can copy this. I don't know what easiest way to copy and paste something. What I'm working with here doesn't really matter. All I want is something that'll allow me to zoom in. Right, I'm using whatever, a pretty cheap way to zoom in on this location. Right, so this V1 little plus sign shows me where the pixel is that I've labeled. It's the center of that little cross, and this VT1 is the label that I've put on that location. Okay, so here's VT1. VT1 is the name that I've given it. So it's vegetation tree location 1. This is a location in the name. This code will place this name and put a little X mark on that location. So let's see how that's done. So this is where this copy is. I want to take the clipped image and make a copy of it. If I didn't do copy, when I do this, when I modify this image label, it will modify the original variable, right? It just really what it does without the copy command there, it takes that image labeled, and when I say, or image clipped, and when I say image labeled equals image clipped, it really says image labeled is now a new name for image clip, but it refers to the same block of memory. But doing the copy says take all the things that are image clipped, make a new memory, block of memory, and a new array, and put all the information there. Okay, so here it says we're going to make a plot, and we do this so we can set the figure size. We're going to do this with subplots. So 2 rows, 1 column, first subplot. This gets the row and column of the location. This DR is what I was using for delta row and delta column. And I want it to go from whatever my row is, and I want to go from 2 pixels to the left to 2 pixels to the right. Right, so to see what this is doing, we can print that. And so this prints when I'm filling these pixels in with red, says we're going to fill in, actually print this. So this will give me the row and column where I'm filling in with red. This line here says take this row and column and the 3 bands and make them, 1 is highest value for red, lowest possible value for green and blue. So this will make that pixel red. So this says make 198, 178 red, 199, 178 red, 200, 178, that's the pixel up here, that's my main location. So this goes 2 pixels to the left to 2 pixels to the right at 178. So that makes the little horizontal part of my plus sign. This goes vertical, makes the vertical part of the plus sign. So I'm manually changing those pixels to make them red so I can see the location. Now I could do this, which is just make the pixel that I'm caring about red. But if I do that, it's hard to see that single red dot, but that's just the pixel, the 1 pixel by itself. So now we're going to do the im show. So we're going to show the image now that we've added the red to it. And this plt.text says put some text on my image, go to the row, but 10 columns to the right. So I move a little bit to the right to put this text. Name is the name that we've given for this location. Give a text size, a color. This alignment, horizontal alignment, vertical alignment says we're going to align this text to the left side of the location and vertically like centered where we told it to go. And then row and column, so that's our X label and Y label on our pixel. And now here's the spectra part. We take the image array, this row and column, and all the bands. So this piece gives us the values for the spectrum at this location. We're going to give it a name, a label, which is the name VT1. And so here's a plot of that spectrum. And so the wavelengths go on the x-axis, and the vertical axis is going to be the reflectance, which are the values given in the array. I like to put a grid when I plot a spectrum so I can see, horizontal and vertical values. And then we want to label the X and Y values. And so there's our spectrum. And this is, we've talked about this a little bit. This is a typical vegetation spectrum. We see a little bump up here around 650. There's a fair amount of noise in it. It's not as smooth, right? That's from just the quality of the sensor. This bump here, and there's a bump here, that both have to do with water bands, which we're going to talk about. So there's interference from the atmosphere, which create this weird spikes. We'll talk about that more in detail further in the course. This is going to be a function. So what we want to do is we want to be able to repeat this, but feed in not just one location and name, right? It's a pair, it's a location together with a name, but a bunch of locations and give them names and show them on the image. So what we're going to do is we'll create a function where you give the function the array, the RGB for the array, for the image, the full array for the image, and this locations, LOCs. A lot of times when you make a function, this is how we make a function in Python, we do def and then a space, the name of the function, and then here's the inputs for the function, and then you need a colon. And then nice commenting. After we declare a function, after we make a function, we have a little statement of what the function does, and then what the inputs are, and then if there's outputs for the function, we'd want to put those as well. I guess I didn't put in like what this thing is into my list of inputs, and I probably should have. And this locations or LOCs, that's going to be, each LOC is a list of length 3. The first item in the list is going to be the row, which is an integer, the column also an integer, and the name, which has to be a text. Okay, so what we do is the same code as above, but we're going to iterate through all the values that are in LOCs. So this says iterate through LOCs. For each value in LOC, it's going to be a list. I guess it's actually length 4. And with the row and the column and n. Which I guess we'll see what n is in a minute. Oh, n is the name. So, okay, so it's row, column, name, and then the color. So this allows us to put a separate color for each of the pixels that we're going to label. Okay, that makes sense. So, row, column, name, color. Right, so I should have that in my documentation. And multi-dimensional NumPy array for the spectral image. Oh no, this one's the multi-dimensional one. This is going to be a 3-dimensional NumPy array for the visual RGB. So that would be better documentation. All right, so we can create this function. Okay, so now this has created the function, but it hasn't added anything to my image. It hasn't done anything. Or it hasn't run the function. So what I need to do is to create a list of locations, and then I'm going to feed these locations into that function, and it's going to plot the image visually, and it's going to plot the spectra for those locations. So, all right, so there's my spectra. And if I said, I want a pixel that's right here on the lawn, right? So 1,000, maybe 1,100, I don't know. Row 150, it's actually column 150. So if I want to add another pixel to this, I can add this to my list, and it's row 1,100, column 150. This is a lawn in front of the Capitol. And if I want to make it a color, these are names for colors. So if in matplotlib, you get a list of the named colors. Those images might have been good. So, but I can pick a name. I don't know. I'll call it purple. So I'm going to get the color purple. So this lawn be a little weird. I usually like to give a color that corresponds to the wherever I'm putting that. But okay, so now I've got a pixel on the lawn. It looks like I need to move that up a little bit. So maybe I call it 155, 158. And so now I have a lawn pixel. Its location is shown in the image. And down here, the purple line is going to be my lawn pixel. And you can see that follows pretty closely to the yellow. And the yellow was veg grass 1. Where was that? So this pixel over here, VG1, is very close to my lawn pixel. Right? You can see the spectra match pretty well. VG2, which is the cyan, which is up here, it's a probably grass in a different area. And judging by this looks, maybe it's a little different grass. Maybe it happens to be in a bush. Whatever. It's not clear. It's not obvious like what the difference is. Different types of grass. Where the red and green, you can see those track closely to each other. The red and green are our veg trees. And then the monument is the blue, and that's very different from the other spectra. And based on a little hint we had or a discussion, the 2000 to 2500, this range, is important for minerals and rocks. And so looking at the monument, this sequence of kind of rise up to a peak, drop to a fall, rise to second peak, and dropping off, that sequence is indicative of the type of cement or material that's in the monument. That's about everything we have. I hope that was helpful, getting used to some of the coding that we're going to be using and working with images in Python. Have a great day.